So, hey everyone, this is our final video that I want to cover in a series circuits context, and it has to do with some troubleshooting, and that didn't work, and something that we call open or opens and shorts, right? So, to begin with, let's define what an open and what a short, what they are. I lost my pen. There it is. Thank you. All right. So an open is a break in a circuit that fully prevents current from flowing. Mathematically, the resistance of an open is infinite ohms. All right. So it's infinity. There's no value, or the value is so big that you can't tell the difference. All right. A short is when 2 points or two points are forced to the same potential. In other words, the short has zero potential difference. And mathematically, the resistance of a short is 0 ohms. All right. So these are two specific aspects that happen in circuits. And when we understand them and what they end up doing in a circuit, it helps us to troubleshoot when we observe problems. Okay. So again, this is a massive topic, especially in the context of series circuits that we've been talking about, but they're very useful, extremely useful. All right. So for one thing, here's an example. When we have a series circuit, so one thing we know about series circuit is they have the exact same current throughout the whole circuit. Now, if I have an open in the circuit somewhere, meaning there's a break somewhere, well, we instantly know that there'll be no current. So if I go to measure a current, well, the current through that circuit will be 0. And I go, oh, there must be a break somewhere. There must be an open circuit somewhere, an open somewhere that's preventing the current from flowing. All right. A short, on the other hand, if we've got a series circuit, is, well, we can calculate what current we're expecting. And so when we know that as resistance, the total resistance goes down based on Ohm's law, voltage stays the same, the total voltage stays the same because we're not adjusting it. If my resistance goes down, well, then the current goes up. There's less to oppose the electrons, so the current goes up. So when we do our measurements and we notice that the current is actually larger than our expected current, well, then we can kind of suspect that, oh, wait, either we made a mistake in our calculation, or number two, maybe one or two of our resistors are shorted out. All right. So let's look at a couple of examples. Let me just add, before with that, let me just add a couple of ideas. So I through an open equals 0, okay, because there can't be. So I as in current, and voltage across an open is, or sorry, I should just say equals V total, depending on the circuit. So you would actually see the total voltage there, and we'll sort of prove that with an example. For a short, I through a short equals a larger value than expected. And can be equal to infinite amps, which is really, really bad, obviously. You would burn your cable or your wire or whatever. And so this is a possibility depending on how the short happens. The V across a short, and I've already mentioned that, equals 0 volts, right? So they're really the opposite of each other, right? And I also mentioned the resistance of an open is infinite resistance, and the resistance of a short is 0 ohms. Okay, and so let's look at an example and see how this can kind of help us when we solve something. All right, so let me draw a circuit. We'll keep it simple for the moment. 10 volts, 200 ohms, 800 ohms. All right, so typically we've seen this problem. So if everything is okay, then this is VR1, VR2, R1, R2. Our current is this way, so I plus minus. So if everything's okay, VR1 will equal 2 volts and VR2 will equal 8 volts, right? But if, say, R2 gets shorted, what happens? Right? So instead, we have something like this happens. We short out, we have a wire that forces the potential difference here and there to go to the same thing, right? So now VR2 is forced to 0 volts because I'm forcing the potential here and the potential here to be equal because there's a wire right here, okay? That means our current I has changed now, all right? Because when an electron comes right here, it has two choices. It can take this road that has 0 resistance. It's easy, nothing stopping it, as opposed to this one, which has opposition to it. So every electron will choose to go this path. So when R2 gets shorted, the circuit then really looks like this. And R2 disappears, and we only have R1. And so VR1 now is only 10 volts, and I is only 10 volts over 200, which equals something I should be able to do in my head, but not at this hour. So yeah, 50 milliamps, right? Just for completeness sake, the I up here, just so we can have the the comparison, we have the 10 volts over the total, which is 1000, and that's equal to 10 milliamps. All right, so you could see right away our current has jumped up by a factor of 5 because the 800 ohm resistor was shorted out. All right, when we start talking about parallel circuits, we'll be able to show mathematically that what I said here about the electrons choosing this path that has no resistance over the path that has 800 ohms is always the case. And it can be shown mathematically too that really this 800 ohms basically disappears if it gets shorted out. So now I know if I measure 500 milliamps, I'm like, whoops, wait a second, there's a problem here. Something must be shorted. So I can double check by measuring the voltage across VR2 and I see, oops, 0 volts. That doesn't make sense. It's supposed to be 8, but I'm only getting 0. And double check on VR1, I'm getting 10 volts. Like, whoop, whoa, that's way too much. It should only be 2. So I clearly know that there's a short in the circuit. And because VR2 is 0, that's where the short is, right? Let's look at an example. I don't want to erase everything because I want to be a little lazy. I can leave these values because we can use them. Let's say R2 is going to become an open circuit. Okay, and we'll see what happens. So if R2, whoops, put in black, just that. So R2 is now open. So in essence, that means oh, I didn't want to erase everything. That's okay. I'll just redraw up to R2. There we go. Okay. So now we have an open here. And R2 essentially no longer exists. All right. So right away, we see that I equals 0 amps. No path for current to pass. Okay. But how do we prove that VR2 now equals 10 volts? Well, stop and think about it. We have down here just wire, and we have said that here is our 0 volts because of the ground. So this node here is 0 volts right here, this point. Up here, even though there's no current flowing, there is a potential difference because of our battery. So up here, okay, actually, let me not jump that far, just to make it, just so that everybody sees it. I think we're okay with saying that everything here, that's equal to 10 volts relative to ground, all right? But what is VR1 in this case? Well, VR1 is given by I times R1, correct? I, in this case, hello, is 0. And R1 is 200. So VR1 is equal to 0. So the potential difference here is 0. So really, everything here is equal to 10 volts. So the potential difference between these 2 points in the end is equal to 10 volts. So in a series circuit, if you have an open, that open will always be equal to the voltage across your battery. Whatever voltage your battery or your power supply is producing, you will find this voltage at this point. So I know that that's a big concept. It's a new concept, and it'll take some practice. If it doesn't make any sense, for sure, rewatch this slowly, think about it, do some measurements on your own, and we'll definitely have an assignment to work on to kind of work these ideas through. All right. So there you go. Thanks for watching, and I hope these videos have been useful to you. Have a great day.